Welcome back, everyone. Learning as a hobby here. I wanted to, I know it's been a while since I posted a video. I wanted to, so I got it into my head that I wanted to finish all of the books that I'm going through right now up until chapter 2 at least, which means I'm putting Spivak on hold for a bit. I remember chapter 4 is kind of long in that section. Maybe I'm just putting it off because it's kind of a tedious chapter and maybe I'm just procrastinating doing it. But I wanted to at least get up to chapter 2 in the differential equations book. We already got up to chapter 2 in the Taylor book, but I still have Schifrin that I got to get to chapter 2 on, and Linear Algebra Done Right by Axler. There's only one section left in chapter 1 there, so I think I'm going to focus on getting up to chapter 2 in this one and in Axler first. Then I'll get to chapter 2 in Schifrin, and then we'll come back to Spivak. That's just what I feel like doing, so it's what I'm motivated on doing. And I guess, well, I'll talk more about stuff like that when I'm going to make a sort of update to the sort of a state of the channel video in a little while, so maybe I'll talk more about that later. But anyway, let's do section 1.4 in the Simmons book for today in this video. So if you recall, we're going through Simmons differential equations textbook. Chapter 1, section 4 is on basically like exponential growth and decay models, growth, decay, and chemical reactions. So let me bring up my notes that I took for this chapter, and we'll just go through it. It's actually kind of a short chapter. It's just there's a lot of examples, and actually the exercises, while they are all given by exponential models, you're solving differential equations that give you exponential models. The problems that he gives in there are actually pretty interesting and pretty varied. So I've already done the work for that, so I'll make a video about the exercises after I do this one, I think. So let me bring up my notes. For the summary, and we'll get into this. Let's move my camera out of the way. Okay. So like I said, this section is on exponential models. So it starts out with reminding you of the definition of that special number denoted by the letter E, 2.718, yada, yada, yada. It's intrinsically related to growth processes. And it's one definition you could take for E is it's the limit of this expression here. So it's the limit as n goes to infinity of 1 plus 1 over n all raised to the nth power. Or if you prefer, it's 1 plus h raised to the 1 over h power as h goes to 0. So take the limit as h goes to 0. That's the definition of that number. And then if you recall the exponential function, which looks like this, it has base e. This is a special function because it's the only one that is equal to its own derivative. That's non-constant. Right? So y equals e to the x. It's a solution to the differential equation dy over dx equals y. Okay? It's the function that is its own derivative. More generally, if k is not 0, then this family of functions here is the solution to the differential equation dy dx equals ky. All right. And furthermore, they're the only solutions. And one of the exercises in the exercise set asks you to prove that. So we'll do that in the video about the exercises. All right. And then he says there's a surprisingly wide variety of applications of these facts to a number of different sciences. And the rest of the chapter is basically giving some examples of places where this type of exponential model occurs. So we'll go through some of the examples he gives here, and there are more examples that he gives in the exercises. So like I said, actually in this section, the exercises are kind of fun. I actually enjoyed doing the exercise set a lot for this section. All right, first example he gives is in continuously compounded interest. So if $P is deposited in a bank account that pays an annual interest rate of 100K% compounded n times a year, Then after t years, the accumulated amount is a equals p times 1 plus k over n raised to the nt power. That's called the compound interest formula, which you probably remember from your algebra course or your pre-calculus course or whenever you took that, maybe in high school. We want to look at the limiting case where, so in this formula here, n represents the number of compoundings per year. If you want continuous compounding, what that means is you take n, you let n go to infinity. So you're compounding interest infinitely often. Okay, so in that case, a is equal to the limit as n goes to infinity of this expression here, and then using the properties of limits and the definition of the letter of the number e, then a is equal to p e to the times e to the kt when you take the limit. All right, so we get this exponential growth model here, and then he's just defining what k represents. So here, if dA dt is ka, that implies that 1 over a dA dt is equal to that number k, which you can think of as the fractional change in a per unit time. So that's the first example he gives. Second example is with reference to population growth. Again, if you've taken pre-calculus or whatever, you've done problems like this before. So hopefully at least some of these examples will seem familiar to you. Maybe some others won't. But if we have X0 bacteria are placed in a nutrient solution at time t equals 0, and that X equals X of t is the population of the colony at a later time t. If food and living space are unlimited, and if as a consequence, the population at any moment is increasing at a rate proportional to X itself, we can write down the differential equation Tx dt equals k times X. That's so the rate of change is proportional to the population size at time t, in other words. And then if you solve this again, we already saw, he stated above that the solution is this. You can solve, this is an easily solved differential equation by separating variables, as are all the differential equations in chapter 1. Okay, so you get an exponential growth model for the population there. This population growth model is not realistic for long time periods because population, in the real world, populations don't grow exponentially forever, right? Because there are limitations to space and resources, etc. But anyway, here's an example that's like that more realistic example in the exercises. We'll look at that when we get to that video. All right, also he gives an example of radioactive decay. So in a first order chemical reaction, a certain molecule that decomposes into smaller molecules does so at a rate proportional to the total number of molecules present in a unit of time, and the rate is unaffected by the presence of other substances. So that's what is meant by a first order chemical reaction. Suppose, for instance, that X0 grams of matter are present initially, maybe some radioactive substance or something, and decomposes in a first order reaction. If X is the number of grams present at a later time t, then negative dx dt equals k times X. Here k is greater than or equal to 0. In other words, this is a decay reaction or decay model. K is the fractional loss of X per unit time. And again, if you can solve this differential equation by separating variables, and you get this exponential decay model here. So xt equals x0 e to the negative kt. Again, something that you've seen before, hopefully. Next example is mixing. A tank contains 50 gallons of brine in which 75 pounds of salt are dissolved. Beginning at time t equals 0, brine containing 3 pounds of salt per gallon flows in at a rate of 2 gallons per minute, and the mixture, which is kept uniform by stirring, flows out at the same rate. When will there be 125 pounds of dissolved salt in the tank? And how much dissolved salt is there in the tank after a long time? Meaning as t goes to infinity, so take the limit, in other words. All right, so we set up our differential equation here. So here we have actual numbers to work with. So we have, we had water coming in that contains 3 pounds of salt per gallon, and it was coming in at 2 gallons per minute. So this is the rate that salt is flowing in. So you have 3 pounds per minute coming into the vat or whatever the container is. And then you have the amount of salt in the tank at time t, which is x of t, divided by the 50 gallons that are initially in the tank, times 2 because it's flowing out at the same rate as the salt is flowing in. So this is the amount of salt that's flowing out at time t. Right, so it'll be x over 25. Just simplify this thing here, and that gives you the rate that the level of salt is changing at in time. So dx dt is 150 minus x over 25, and we can easily solve this differential equation by separating variables, which I'm doing below. Right, so 1 over 150 minus x dx dt is 1 over 25. Find your antiderivatives, which gives you, when you simplify everything, this expression here. So this family of functions here, x of t equals 150 minus c times e to the negative t over 25. And then finally, we can figure out what c is by plugging in the initial value. So at time 0, there's 75. They said there were 75. Was it grams or pounds? I forget what they said. 40 pounds. So there's 75 pounds initially. So set that equal to 75 and equal to the model, and you can solve for the value of c, which gives you, oh, I just realized something. There's a typo here. This should be a 0 here. And so then you could use that to solve for c, and when you do that, you get that c is 75, which is the initial amount of salt in the tank. Okay. That gives you the model, which I have written down here. X of t is 150 minus 75, e to the negative t over 25. And we can use that model to solve whatever problem they want us to answer. So then 125, so they want to know when it's going to equal 125 pounds of salt in the tank. So set the model equal to 125. So 125 equals 150 minus 75, yada, yada, yada. Solve that for t, and you get t is equal to 25 natural log of 3, and then just plugging into a calculator to get an approximation. It's approximately 27 minutes. I rounded to the nearest minute, so it's something like 27 point something minutes. I forget what the decimal was. And then lastly, they want to know what the limiting value is. So when as t goes to infinity, after a long time, what is the sort of steady state that arises? The amount of salt that is going to be in the tank, for all t past some finite value. So take the limit as t goes to infinity. You get 150 minus 75 e to the minus, sorry, that's what you take the limit of. Notice that this goes to 0 as t goes to infinity. So you're just left with 150 pounds. Right. So after a long time, the tank should contain a constant amount of 150 pounds of salt. Right. And I think that's the last example, but there is one last thing he talks about in the section, but he doesn't do it as a problem. There's sort of like he gives sort of an account, a historical account of the development of radiocarbon dating. So it's only a couple pages, so I figured I'd read it to you guys because it's interesting. And then I'll finish this video, and then I'll get to the exercises for this section. All right, so here's his account of the development of radiocarbon dating. This is what's his name? George Simmons talking. So the ideas discussed in example 3 are the basis for a scientific tool of fairly recent development, which has been of great significance for geology and archaeology. Here he's in example 3, he's talking about the radioactive decay problem that we talked about a minute ago. In essence, radioactive elements occurring in nature with known half-lives can be used to assign dates to events that took place from a few thousand to a few billion years ago. For example, the common isotope of uranium decays through several stages into helium and an isotope of lead with a half-life of 4.5 billion years. When rock contains uranium is in a molten state, as in lava flowing from the mouth of a volcano, the lead created by this decay process is dispersed by currents in the lava. But after the rock solidifies, the lead is locked in place and steadily accumulates alongside the parent uranium. A piece of granite can be analyzed to determine the ratio of lead to uranium, and this ratio permits an estimate of the time that has elapsed since the critical moment when the granite crystallized. Several methods of age determination involved involving the decay of thorium and the isotopes of uranium into the various isotopes of lead are in current use. Another method depends on the decay of potassium into argon with a half-life of 1.3 billion years, and yet another, preferred for dating the oldest rocks, is based on the decay of rubidium into strontium with a half-life of 50 billion years. Maybe I should say what half-life means because I didn't define it here. Half-life is the amount of time it takes for an initial amount of substance to decay by half. That's what they mean by half-life. These studies are complex and susceptible to errors of many kinds, but they can often be checked against one another and are capable of yielding reliable dates for many events in geological history linked to the formation of igneous rocks. Rocks tens of millions of years old are quite young. Ages range into hundreds of millions of years are common, and the oldest rocks yet discovered are upwards of 3 billion years old. This, of course, is a lower limit for the age of the Earth's crust, and so for the age of the Earth itself. Other investigations using various types of astronomical data, age determinations for minerals and meteorites, and so on, have suggested a probable age for the Earth of about 4.5 billion years. And he has like a, what's it called? Like a note about reference for that, which I'll skip. The radioactive elements mentioned above decay so slowly that the methods of age determination based on them are not suitable for dating events that took place relatively recently. This gap was filled by Willard Libby's discovery in the late 1940s of radiocarbon, a radioactive isotope of carbon with a half-life of about 5,600 years. By 1950, Libby and his associates had developed a technique of radiocarbon dating, which added a second hand to the slow-moving geological clock described above and made it possible to date events in the later stages of the Ice Age and some of the movements and activities of prehistoric man. The contributions of this technique to late Pleistocene geology and archaeology have been spectacular. In brief outline, the facts and principles involved are these. Radiocarbon is produced in the upper atmosphere by the action of cosmic ray neutrons on nitrogen. This radiocarbon is oxidized to carbon dioxide, which in turn is mixed by the winds with the non-radioactive carbon dioxide already present. Since radiocarbon is constantly being formed and constantly decomposing back into nitrogen, its proportion to ordinary carbon in the atmosphere has long since reached an equilibrium state. All air-breathing plants incorporate this proportion of radiocarbon into their tissues, as do the animals that eat these plants. This proportion remains constant as long as a plant or animal lives, but when it dies, it ceases to absorb new radiocarbon, while the supply it has at the time of death continues the steady process of decay. Thus, if a piece of old wood has half the radioactivity of a living tree, it lived about 5,600 years ago. And if it has only a fourth this radioactivity, it lived about 11,200 years ago. This principle provides a method for dating any ancient object of organic origin. For instance, wood, charcoal, vegetable fiber, flesh, skin, bone, or horn. The reliability of the method has been verified by applying it to the heartwood of giant sequoia trees, whose growth rings record 3,000 to 4,000 years of life, and to furniture from Egyptian tombs, whose age is also known independently. There are technical difficulties, but the method is now felt to be capable of reasonable accuracy as long as the periods of time involved are not too great, up to about 50,000 years. Radiocarbon dating has been applied to thousands of samples, and laboratories for carrying on this work number in the dozens. Among the more interesting age estimates are these linen wrappings from the Dead Sea Scrolls of the Book of Isaiah, recently found in a cave in Palestine and thought to be 1st or 2nd century BC, 1917 plus or minus 200 years. Remember, this book was written in 1950, so the dates here are with reference to the year 1950. Charcoal from the Lascaux Cave in southern France. Hopefully I said that right. Site are remarkable prehistoric paintings, 15,516 plus or minus 900 years. Charcoal from the prehistoric moment at Stonehenge in southern England, 3,798 plus or minus 275 years. Charcoal from a tree burned at the time of the volcanic explosion that formed Crater Lake in Oregon, 6,453 plus or minus 250 years. Campsites of ancient man throughout the Western Hemisphere have been dated by using pieces of charcoal, fiber sandals, fragments of burned bison bone, and the like. The results suggest that human beings did not arrive in the New World until about the period of the last ice age, roughly 25,000 years ago, when the level of the water in the oceans was substantially lower than it now is, and they could have walked across the Bering Straits from Siberia to Alaska. And then he has a note here. Libby won the 1960 Nobel Prize for Chemistry as a consequence of the work described above. His own account of the method, with its pitfalls and conclusions, can be found in his book, Radiocarbon Dating, second edition, University of Chicago Press, 1955. So that's the account of radiocarbon dating. There is one problem in the exercise set that deals with radiocarbon dating, which we'll do in, when we get to the exercise video. Let me just stop the screen share for a second. So I'm going to stop this video here. Like I said, I realize it's been a while since I posted videos. I have the exercise set for this video coming up. Then I have, I'm going to do section 1C and linear algebra done right, the summary for that, and then the exercises for that, but probably not today. And then, like I said, I'll make a video giving sort of like an update about, where the channel's at and everything. So, thanks for watching, everybody. Please do like and subscribe if you enjoy watching this content. And crap, I just realized I didn't have this down the whole time. Hopefully the sound is all right. I guess I'll check. If not, you won't be seeing this. If the sound is good, then I'll just post it. But anyway, keep an eye out for the next video coming up. Until then, keep learning, everybody, and I'll see you in the next video.